Zeal Education Society, redefining excellence.
Modeling population is a very interesting application of differential equations. Now, since you have taken a calculus course, you are already familiar with a certain population model, and you call it exponential growth model. If a population grows at a rate which is proportional to the size of population itself. In other words, dp upon dt k into p. Now there are other population models which you may not be familiar with. For instance, the second ones I have written here, it's called the Logistic Equations, and actually a better model for population in application than the exponential growth. I have down another guy here, dp upon dt k into p square, and I don't know proper name for this one, but you call it maybe a blow-up model, because the population blows us in infinite time in this particular model, rather than derive each of these models individually. What I will do now is discuss a general population model from which this equation can be derived, among others. So let's start with the population. Let's call PT, P of t, beta is equal to birth rate. For the population we have a certain number. Now the birth rate is the number of births per unit of population per unit of time. Now a unit of population could be anything from a single individual to 10,000 individual to 20,000 microorganisms or bacteria. A unit of time could be a second or a year or a decade. And similarly, delta is equal to death rate might, and similarly in the same fashion per unit of population per unit of time. Now just to give you some sense of what these quantities might be, for example, you can look up the CDC data on the United States, and I found that in 2009 there were 13.5 births per 1,000 individuals, and that was in a single year, so that would be beta if I to choose the units accordingly. So that would, I should point out a very important things about beta and delta. Beta and delta may be depend on the population size p or the time t. There is nothing that restricts this model to have beta and delta constant, and this is pretty reasonable dependency because, for example, the birth rate may go down as the population increases, because there could be something like a food restriction, or overpopulation may make people less likely to have children. Now, to set up a model for the population, we ask ourselves the same question we usually do when we are trying to derive a differential equations, and that is, how does the dependent variable change when the independent variable change. So the question would be, how much does p changes in some small interval of time delta t. We call that change delta p. It's easy to see that delta p will simply be the number of units of population born in the small amount of time delta t minus the number of units of population that died in the small interval of time. And by the definition of birth rate, death rate, beta and delta, the number of units population born is beta into p into delta minus t, and the number die is delta into p delta into minus t. And delta p is the difference of those two quantities. Now, as usually when we want to turn a small changes argument into derivative, we divide both sides by delta and take the limit as delta t goes to 0. And the result is differential population master population model. The model from which the other population models are derived. That's dp upon dt beta minus delta into p, and I will remind you again here what beta and delta may depend on p or t. That's perfectly okay in this model. Now here I have written just briefly what beta and delta are in each of these models. In the exponential model, exponential growth, beta and delta are constant. For the logistic equation, delta is constant and beta decrease linearly with the population. For this blow-up model, delta is equal to 0 and beta is proportional to the population. Now, just because we can, I had like to throw a little extra something into this model. Suppose we have a fish pond and the population of fish in that point is governed by the population model we derived here. But I like to catch fish, and so every year I catch 100 fish out of that pond. Now my question is, how would I incorporate that into this model? I cannot incorporate it through a birth rate or death rate. I catch 100 fish every year, no matter what the population is, as long as there's enough in the pond. So it's not part of the birth rate or the death rate. So I will include it as what's called a harvesting rate. The harvesting does not depend on the population here. It's just some harvest rate time, the interval of time. So I add this harvest rate minus h delta minus h into delta minus t into the change delta p. Let's give me an extra term on the right hand side of the population model. dp upon dt is equal to beta minus delta into p. So this is the master population model with this little bonus terms of harvesting. To describe a constant draw on the population, such as fishing, and we could also describe a constant add to the population, like a certain number of immigrants who are allowed into a country, or a certain number of fish that are put into a pound in order to stock it.